Welcome once again everybody to this acoustic webinar about the acoustic challenges and simulation processes in the space industry. My name is Marie Cabrol and I'm a senior application engineer at Freefield Technologies, a MSc company. I will begin with this presentation with a slide introduction to the space problematics, which are mainly vibro-acoustic problems, and I will explain what contains Actron for solving vibro-acoustics. This presentation will then deal with the challenges for aerospace application and what to do for modeling them. 2 case studies will be shown as example, and a live demonstration will be done to explicit how to use Actron for aerospace applications. If you have any question, you can ask in the dedicated Q&A session at the end of the presentation. Because the aerospace industry is very diverse, with a multitude of commercial, industrial, and military applications, and for competitive reasons, more and more powerful rockets are required in order to reach a higher lift capacity or in order to go further in the space. For that reason, the launch is a determinant point to leave the Earth, and very high pressure levels are generated around and in the vehicle. 120 to 180 dB can indeed be reached at the liftoff, impacting the health of the crew, because such acoustic levels can permanently damage the human ear. And in addition, it submits the structure of the launcher and the high technology component embarked to intense acoustic fields. These induced vibrations can first damage the vehicle, but also the payload components. So the main challenges of the aerospace industry are therefore to model vibroacoustic problems and predict the vibration levels of structure submitted to intense pressure loads. As a perspective, I first want to show you that Actron is a dedicated tool for the aerospace industry. Actron is indeed a dedicated tool for pure acoustic, vibroacoustic, but also aeroacoustic simulations. Based on the finite and infinite element method, the software is easy to use thanks to a dedicated graphical user interface called Actron VI that is constantly improved and for which every action can be registered and scripted in dedicated sessions. The simulation process starts first with the mesh and the model building, for which we include meshing functions. Then, this is followed by the solver, in which high-performance computing solutions can be used for reducing the cost of the computation. Finally, the post-processing is available in the same graphical interface, where a lot of operators and outputs can be displayed. To go further, Actron stands for acoustic transmission based on finite element method. Firstly, the field is modeled with volume elements for the near-field representation, and free-field radiation conditions are available. First, the far-field can be modeled with infinite elements, and secondly, a perfect matching layer is also available for reducing the cost of the model, especially at high frequencies. Complex structures can be included in a fully coupled model with light or high damping, including a single layer or several layers. Composite materials are also available for which the properties of each ply can be defined separately, and finally connection elements can also be used. Regarding the Actron formulations, different solutions are available like viscoelastic solids, thin shells, solid shells or composite shells. Beam and stiffeners can be modeled, and rigid body, spring and point masses are available with the same formulation than MSc Nastron cards. As an important remark, the dedicated tool Nastron to Actron allows to directly translate a Nastron analysis into an Actron model. Specific to the acoustic modeling, Actron includes porous elements based on the Biot model for representing foam, rock wools, or any other type of porous medium. Both the full modeling, including skeleton and fluid interaction, and simplified models are available depending on the material properties of the porous medium. In addition, isotropic, but also anisotropic materials can be modeled. The dissipated power is accessible in each porous medium, allowing to easily access the percentage of the dissipated power in a multilayered material. Finally, any type of material properties can be frequency dependent, and therefore fits experimental measurements of the porous medium properties. So in general terms, Actron is the dedicated tool for vibro-acoustic problem. And now I'm going to show what the vibro-acoustic challenges for aerospace applications are and what to do for modeling them. I'm going through the different types of external noise sources and the corresponding challenges in the numerical modeling. First, an exterior acoustic field is generated at the liftoff due to the engine noise. This excitation can be seen as a broadband and random acoustic pressure. This excitation is equivalent to a diffusant field, actually. The diffusant field is a random process for which the mean square pressure is the same at any point in the space. In addition, the flow of the acoustic energy is all directions equally probable. This excitation is equivalent to the acoustic field generated in a reverberant room by an omnidirectional source, for instance. For the numerical modeling, the diffusant field excitation along the external surface of the structure is applied to all the points of the finite element surface. And it is made of a combination of stochastic processes. Firstly, a reference spectrum is defined in terms of PSD spectrum, and this one can be frequency dependent. Actron is also compatible with the sound pressure levels available directly from measurements. Secondly, cross-PSD functions represent the interdependency between the processes using analytical formulations. So the global diffusant field is made of these two representations. Then, the second source of vibration is not acoustic this time, but is an aerodynamic load due to the pressure fluctuations along the vehicle. These ones come from small turbulent fluctuations in the boundary layer, which are predicted with a turbulent boundary layer model. As a second type of random excitation, Actron includes turbulent boundary layer models. Indeed, while flying, turbulent scales, which are small, are generated around the launcher vehicle, leading to an aerodynamic unsteady load. These pressure fluctuations are transmitted inside the fairing via the structure. The turbulent boundary layer is actually modeled like the diffusant field I just described previously, and is also seen as a combination of multiple stochastic processes based on reference PSD and cross PSD functions. The difference is that the TBL relies on semi-empirical models. I provide a list of the reference PSD model available in Actron. The Cockburn and Robertson model is especially based on experiments of spacecraft panels subjected to in-flight fluctuation pressures. On the other hand, the cross-power spectrum comes from the spatial correlation functions, either described by Korkos or Effensoft model. Finally, the third type of external source is the structure-borne noise due to the structure vibration and the acoustic transmission. For that purpose, the acoustic insulation performances can be predicted via transmission loss and noise reduction index studies. In addition, the vibration levels and the induced constraints can be predicted and coupled to an acoustic fatigue analysis. Now, if I have a look inside the fairing, I also remark that the carry-on component should be studied carefully. Indeed, all the type of external sources described previously are transmitted inside the fairing, and the embarked satellites, for instance, is also submitted to intense acoustic fields. The first specific modeling challenge inside the fairing is therefore to represent a broadband random acoustic pressure that includes, in that case, some specific masking effects. Indeed, the position of the embarked component inside the fairing has its importance on the repartition of the pressure field along the structure surface. The masking effect is actually due to the installation effects, and the diffuse sound field I described previously cannot be directly applied along the whole satellite surface. I take a small example to have a look to an arbitrary geometry placed in a reverberant room. Because of the geometry of the structure, there are external surfaces that are not loaded by the incident acoustic field. These surfaces are masked because of the geometry of the structure. The diffuse sound field excitation in Actron actually makes the distinction between the conventional model and the diffuse sound field including masking effects. In the conventional model, described in the previous slides, the excitation is applied directly along the external surface of the structure. The reference PSD and cross PSD are described by analytical formulations without taking into account the masking effects. To include the masking effect, the surrounding fluid should be modeled with finite elements. The diffuse sound field excitation is then applied along the infinite surface, and for that purpose, the diffuse sound field is represented by a superposition of a high number of incident plane waves with different orientations. The generation of the plane waves is automatically done around the structure and equally spread around a reference sphere. The random character of the excitation is then modeled by sampling random phases of the excitation. The random excitation therefore becomes the combination of different deterministic results for which the phase of the plane waves change. One realization of the random process provides one result, and the PSD values are obtained by summing the square results. Therefore, the convergence of the PSD result depends on the number of samples considered during the Actron computation. I draw your attention on an important point with the sampling process. Only one Actron calculation is needed thanks to the multiple load analysis. The second specific modeling challenge inside the fairing concerns the viscothermal effects induced in thin air layer. Indeed, neglecting the viscothermal effect could lead to an overestimation of the acoustic pressure excitation along the structure and therefore predict high vibration levels and maybe the structure break, although the structure was originally well dimensioned. When the dimension of the problem becomes very small compared to the acoustic wavelengths, viscous and thermal dissipation actually occurs in the fluid. The acoustic waves are locally slowed down and damped out, and these effects are important in small cavities or thin air layers. The main challenges of the numerical modeling are to be able to compute these effects in arbitrary geometry with an efficient computational process. The distance-based linearized Navier-Stokes Fourier model should be used for any type of 3D geometry at rest. It makes an approximation of the viscous field using a pre-computed wall distance field. The first step computes the wall distance field, which is very rapid inside Actron, and the second step computes the acoustic propagation, including the viscothermal losses. So I have demonstrated that, above all, aerospace applications are vibro-acoustic problems with numerical modeling challenges. Once the numerical model is built, there are different solution approaches for solving it. First, the direct frequency response is useful for complex and high structural damping models, including porous materials, for instance. This approach better suits for predicting the acoustic transmission performances of multilayer materials because of its cost. The model frequency response is useful for reducing the cost of direct computation and solving large structure with low damping and without post-medium. Finally, the hybrid frequency response merges the benefits of the direct and the modal approaches for solving a fully coupled vibro-acoustic problem, including the modeling challenges specific to the aerospace applications. To see in deeper details what is the hybrid method in Actron, it actually relies on intermediate results provided by external tools for modeling the structure. The structure is in the modal coordinate system thanks to a third modal extraction analysis that can be performed with external tools like Actran or Actron, ANSYS or Abacus. The structure is then imported in Actron and the model is made more complex by including specific acoustic excitations and components. For instance, viscothermal effects and masking effects are included in the Actron analysis and modeled in the physical coordinate system. Finally, a hybrid calculation is performed with Actron for a fully coupled vibroacoustic study, including a structure in the modal coordinate system and acoustic components in the physical coordinate system. Thanks to our automatic and adaptive acoustic components, the exterior field is not necessarily meshed by the user. Indeed, included meshing tools are available in the graphical user interface and in the Actron solver. I make a small parenthesis about the simulation process for acoustic fatigue that could be useful for aerospace applications. The output of the Actron computation, resulting of a modal frequency response including a diffuse sound field excitation, could be used in the MSc fatigue software for computing the durability of inner components based on the predicted stresses. Two case studies are presented in this section. The first case was studied in collaboration with EADS. It consists in modeling the equipment bay of the Ariane 5 vehicle submitted to a diffuse sound field in the modal coordinate system, and we compare the predicted vibroacoustic response to experimental measurements at several accelerometers locations. We published a paper at the ECSSMT conference where we demonstrated a very good correlation with the measurements up to 2000 Hz. The second case was studied in collaboration with Dutch Space. It consisted in modeling the structure of the folded solar panels inside the fairing. A modal extraction of the structure was performed, and we compared the results without and with the modeling of the viscothermal losses in the thin air layer present between the panels. The diffuse sound field was applied along the structure's surfaces without masking effects in the first time, and two types of boundary conditions along the free surface of the air layers were studied. We first identified the influence of the air layer modeling that reduced the vibration levels measured at the acceleration points. So with the air layer, let's look at the blue curve, compared to the model without viscothermal losses, that is the green curve. However, the first results were originally high compared to the measurement in black, even if we identified that the viscothermal effects as its importance. Then we included the masking effects by modeling a surrounding fluid domain and applying a diffuse sound field made of plane waves on the infinite surface. The final results in gray benefits the experiments in black, demonstrating the importance of the masking effects in the prediction of the vibration level for embarked components. As a demonstration case, I have chosen a simplified antenna for illustrating how to model a fully coupled vibroacoustic problem, including masking effects in the diffuse sound field excitation. The antenna is first modeled in MSc Actron and contains different components. Shells and composite properties are used for modeling the structure in 2 dimensions. Connection elements are included with C-less and C-bush cards. And the degrees of freedom are fixed with SPC cards that constrains the displacement and rotations to 0 for ground nodes. The modal extraction is performed with MSc in Actran using a SOL 103. The modes are stored in an OP2 database that is called the modal basis. This modal basis is then included in an Actron computation in which specific features for acoustic modeling are used. The Actron model therefore starts from the Nastran modal basis and the Nastran mesh of the structure, and the structure is fully represented in the modal coordinate system. A hybrid physical model strategy is used for modeling the surrounding air and the far-field condition. Then the coupling between the structure and the finite elements of the surrounding acoustic domain is ensured thanks to a non-compatible interface. The diffuse sound field is then applied along the infinite element surface with the resultant pressure of a high number of plane waves. The fluid retraction on the structure plus the masking effects are therefore well accounted for using this strategy. I draw your attention on the Actron meshing capacities that allows to directly create the acoustic mesh from Actron VI, or to use the dedicated exterior fluid components that automatically build the exterior fluid domain during the Actron calculation. For further information, I invite you to have a look at the dedicated webinar about adaptive acoustic radiation analysis with Actron. For simplicity reasons, I am loading directly the full vibro-acoustic analysis inside Actron VI to show you the analysis content. In Actron VI, the data tree panel on the left side of the graphical interface is organized in several nodes. The first node, the topologies node, contains the finite elements, which mean the mesh of the analysis. In this one, we have first the mesh relative to the structure and the mesh related to the external fluid. The analysis node then contains the Actron analysis, which is a direct frequency response in this example. Here are described the different components of the analysis, the boundary conditions, and the post-processing operators. In the model, the structure is representing with a modal elastic component based on the mesh used during the Nastran modal extraction. The modal elastic component in Actron is based on the modal basis that is read in the OP2 format, for which we consider the first 218 and 19 modes. A global damping coefficient is applied to all the modes and done on the stiffness matrix in the example. The components points to a domains that allow to link the something from the analysis to the topology. In this modal basis component, the domain refers to all the element sets of the structure, no matter their dimension. Then, the surrounding acoustic domain is represented in an finite fluid component that refers to fluid materials in which the default properties of the air at 18 degrees are used. Then the component relies on the domain in which the 3D element set is defined. For the non-reflective boundary condition, infinite elements are defined along the external boundary of the finite fluid, and these infinite elements are characterized by a coordinate system for which we fix the center and the system of axes. Then the interpolation order allows to drives the accuracy of the infinite elements for representing the far field actually. In order to couple the acoustic component to the modal elastic component, we use what we call an interface. The interface allows to propagate the degrees of freedom from the structure to an acoustic boundary condition, and conversely for taking into account the retroaction effects. The interface relies on two coupling surfaces, one for the structure and one for the acoustic. These coupling surfaces are defined also in the model, relies on the specific element sets. For the structure, it is actually the same mesh than the structure mesh. For the acoustic coupling surface, it represents a wrap of the structure surface and is actually the skin from which starts the volume elements built around the structure. The wrapping of the structure could be directly done inside Actron VI thanks to the shrink wrap function. As an excitation, we apply a sample random diffuse field along the infinite surface. The diffuse sound field is made of a plane wave decomposition that is activated, for which the plane waves are generating thanks to a reference sphere, which is characterized by its radius, its origin, and pole direction. And we sample the excitation into 20 different samples of the phases of the excitation. So remember, it's a random excitation that is representing with several deterministic results, and the convergence of the calculation is ensured after a certain number of samples. Once the analysis is done, I can define the different post-processing components. So there is first an output frequency response function that allows to write the frequency response functions in the PLT file. There is one for the deterministic results and one for the PSD results. That is actually a combination of all the different load cases contained in the first file. By default, the file contains the global quantities over all the domains used in the analysis, which are quadratic quantities. Then post-processing components can be used in order to output local indicators. First, accelerometers are defined at certain points along the structure. So if I have a look, I can show the location of the accelerometers there. You can see them here. So I request the solid acceleration in G unit in the example. Then I also output in the C-bush and C-less elements the element forces in these 1D element sets. And I look at the resulting forces in the SPC nodes also. Finally, I define some storage elements, which are actually finite elements contained in the structure mesh and situated close to the connection elements, where I have a look at the von Mises stresses. That's for the frequency response output. Then I also define a map that is requested to write down the von Mises stresses along the surface of the dish. The results are exported in an NFF database, and we output the results at specific frequencies that are defined in the properties of the direct frequency response analysis. So the global properties of the direct frequency response are specified directly here, where I can put the frequency range of the analysis that starts at 20 and at 700 with a frequency step of 20 Hz. And there are also specified here the frequencies where the map is output in order to reduce the amount of data written during the computation. As example, I can show you that as your Actron analysis is based on Actron results, you can have a look at the modes firstly extracted by the Sol 103. So for instance, I can have a look at the modal displacements outputted by Actron. Here it is. I can also plot the deform operator in order to have a representation of the deformation. And obviously all these results are available at all the agent frequencies of the modal extraction. Here it is. It's also possible to make an animation of the structural vibration for a specific frequency. Okay, small parenthesis about how to visualize mode results in Actron VI directly. So once the model is completely defined, I can launch the computation directly from Actron VI, specifying a memory consumption and eventually a frequency parallelism. The log of the computation is then displayed on the below part of the Actron VI interface. So for this demonstration, I killed the computation in order to show you all the results. First, I can have a look at the frequency response function. So from Actron VI, I can access the PLT viewer interface, which allows to load the frequency, the PLT file actually. In the example, I have prepared a session that allows to retrieve directly a certain amount of results and plot automatically some results. So I can load the session. Yes. So have in mind that at any time you can retrieve your work, either from Actron VI or from PLT viewer. And in addition, you can also use the scripting capacities for efficient pre- and post-processing operations. So in the example, I have plotted a different types of results. The first figure here shows the PSD of the kinetic power that actually represent the global level of vibration of the structure. For instance, I can identify that at 100 Hz I have a higher value compared to the other frequency, which means that globally the structure vibrates more at 100 Hz. Then if I have a look at local indicators, I can also retrieve the acceleration in G units for all the nodes at which I outputted the results. I also plotted the von Mises stresses that I outputted on the first ply of the composite properties that were output in some elements of the dish surface. I also output the element forces inside the C-bush and the C-less elements. And finally, I also retrieve the forces in the SPC nodes. In PLT viewer, as for VI, you have a tree on the left side, which is related to the results available in the PLT file imported in the PLT viewer. First, you can retrieve the results by domain, which means that you have global results, for instance, mean square pressure in the acoustic components. Then you can retrieve the local indicators, for instance, the element force inside all the C-less elements, or the element force inside all the C-bush elements. plus then the von Mises stresses inside the composite elements of the dish, and finally the solid accelerations inside the accelerometers defined in the analysis. That was for the frequency response function. Now, if I have a look at the maps, I can import the NFF database generated by the output map. So for that, I import the NFF mesh. That is a mesh that actually also contains results. So NFF is the default format for Actron. And here I can export the results in terms of PSD. So I have the surface of the dish, and this contains the von Mises stresses I have requested during the analysis. So I can show the results in terms of norm as a map and not a deformation in that case. And I can use the log scale in order to have a better representation of the results. The results are available at each frequency at which I wanted to output the results. By default, the results are outputted at all the frequencies, but you can choose to specify only several frequencies in order to reduce the amount of data written during the computation. To conclude about this acoustic webinar, Actron can be used for predicting the vibro-acoustic behavior of realistic aerospace's components. Indeed, it includes vibro-acoustic features. The full vibro-acoustic coupling can be solved with different solution approaches, and the modal and hybrid strategies especially allows to reuse existing modes exported by external tools. Thanks to the hybrid strategy, Actron fits the need of the space industry and allows to include the modeling of a diffuse sound field first, but also it has a solution for accounting to the masking effects. It also includes a unique solution for including the viscothermal effects, and this very easily thanks to a two-step approach. The Actron outputs allow for a full understanding of the physics involved thanks to the export of forces, stresses, strain, displacement, or accelerations, for which the information on composite cards, for instance, can be available per ply or as homogenized quantity. Finally, selective maps are also available in order to reduce the amount of data written by the calculation. Thank you everybody for assisting this acoustic webinar about aerospace applications. I invite you to have a look at our other acoustic webinars.